Welcome back. So we were talking about SGD with momentum. We talked about the bias variance reduction or bias variance trade-off perspective, if you will, and we established this theorem that specified the rate at which SGD momentum algorithm finds a first-order solution. So let's briefly talk about the main idea behind the proof. Okay? And the main idea is that we're going to define what we call a potential function, and we're going to track its evolution over time. Okay? So potential functions are basically functions that are, let's say, bounded from below. Okay? So without loss of generality, we say that they are always positive. Okay? And as you are updating, let's say, your parameter, or as the algorithm evolves, you are reducing the potential function. Okay, so therefore, given this property of the potential function, you may recognize that we have actually worked with potential functions before. Okay, so for instance, we talk about the difference between our solution and the optimal solution when we analyze SGD and stochastic SGD and gradient descent for convex and Lipschitz function. So this was basically our you could call it a potential function. It's non-negative, and it is actually, let's say, reducing as your algorithm converges. What we did when you analyzed those two algorithms was basically we studied the evolution of this potential function. Okay. Also, for a smooth function, we talked about the loss value. Okay. So this was basically the potential function we used implicitly, if you will, when we analyze the stochastic gradient descent. Again, this is something that is non-negative, okay, and it is sort of reducing. It is decreasing as my my algorithm is working its way to find a solution. Okay. And a reminder about this notation: F star is basically the optimal loss value, okay, which is 0. Many times, or near 0 many times in the context of machine learning and deep learning. Okay. All right. So let's talk about this case, because this is again the setting we are working here. So a smooth function that are not necessarily convex. What we did previously when we analyzed SGD and gradient descent was that we actually look at, again, the evolution of the loss, meaning that what's the difference of the potential function at one time and the previous time. Okay. So this was basically simply the difference of the loss functions previously, and we studied that using the LS smoothness as well as the simple form of our algorithms. Okay. Now here's a template that I would say is broadly applicable, that for more sophisticated settings or more sophisticated algorithms, such as SGD with momentum, where we are not only updating the parameter to find a solution, okay, or reduce the loss value, but we are also performing, let's say, gradient estimation. Okay, so that's basically what we are doing, as we talked about previously. So it is useful in those cases to augment basically the potential sources of errors, such as gradient estimation that we talk about, with, let's say, a simple potential function such as the suboptimality gap. Okay? And this is exactly what we're going to do here. So we're going to define a potential function which has two components. The first component is the expected suboptimality gap, exactly what we dealt with when we analyze SGD. But we are going to add basically this source of error, which is the gradient estimation error in this case. And I'm going to add some constant C sub e. So this is a constant which we have to determine when we analyze the algorithm. So it's a constant we're going to, if you will, tune to make sure we get convergence guarantee. Okay, so you don't know this beforehand, I would say. Okay, so after defining the potential function, we're going to study its evolution, and by that we mean we're going to sum over its consecutive differences. Okay, so again, sum over time phi t plus 1 minus phi t. Okay. So this is, and the reason we are doing this is because we want to leverage telescoping sum that we have again seen numerous times in the class before. So this is basically going to telescope. So it means that I'm going to be left with the last term minus the first term. Okay. So when if we look at the basically the form of our potential function, and using the fact that the function value at wt plus 1 is larger than the optimal function value, we can lower bound this difference. So we can basically establish the following lower bound. The optimal loss value minus the initial loss value, okay, minus the initial, let's say, gradient estimation error. Okay. So that's basically the first step. You define the potential function by integrating the source of error, and then you basically just look at the difference of the last and the first iterate, which is equivalent to some of the consecutive differences of the potential function. Okay. The next step is actually to leverage the form of our potential function to treat this term differently. Okay. So in the first step, we got a lower bound for this difference. Now we're going to try to get upper bounds for this sum. Okay. So again, using the form of our potential function, there are two terms here. So one term is basically sum over the differences of two consecutive parameters loss, and the accumulation of the gradient estimation error. Okay. Now we established two lemmas when we analyze SGD with momentum. So one lemma use a smoothness to basically relate this term, the gradient estimation error, as well as the norm of the gradient, which is essentially our notion of convergence. So we can use that lemma to handle the first term. We had another lemma on the evolution of the estimation error over time, and we can use that to treat the second term. Okay. So the second lemma in particular had established that the error evolves in a very nice way, such that the error at one time is some constant which is strictly less than 1, very crucial, times its current version plus some other terms. Okay. So this nice property that the next version of my error is a constant less than 1 times the current version plus other terms is something that we can leverage to ensure we can establish our basically a nice bound on our convergence error by finding a good constant C sub e. So in particular, the fact that I have this term here ensures that there is a constant C sub e. So if I didn't have this term, if beta or whatever coefficient I have here was not a circle less than 1, I could not find any constant. So that's why it's a very nice property of our error function, which again arises from the way we are updating our parameter, the way we are updating the momentum vector. Okay. So there you go. That's the second step. So first step, define the potential and then lower bound it. Second step, you upper bound the basically the sum, the evolution of the potential, by leveraging some lemmas that you have to establish by essentially leveraging the property of the loss function, in this case LS smoothness, as well as the properties of the algorithm. For instance, the fact that we are updating our parameter using this first order update, as well as the our update for momentum, which was basically beta mt plus 1 minus beta gt. Okay. So using these properties, we'll be able to carry on with this proof. Okay. Now, there is a mention in this idea of a potential function and the fact that you can augment it, the source of errors in the definition of the potential function is that this is a template that you can see in different learning settings as well. Okay, so not necessarily analyzing SGD with momentum and gradient estimation, but as we'll see in a few more examples, in other scenarios where you are doing some sort of estimation. Okay, not necessarily gradient estimation, but could be something else. And we're going to talk about it in the context of communication compression as well as distributed deep learning. So with that then, let's conclude our discussion on momentum. And as we saw, we talked about the bias variance perspective into momentum, and we're going to use that as a segue to talk about other techniques to reduce the variance potentially even more effectively. I'll see you in the next lecture.